Hello everyone, and thank you for being here. So today I'm going to be talking to you about how we can place constraints on reheating to standard model particles using Planck data if the Higgs behaves as a light spectator field during inflation. So I'm going to start my talk with some basics about how inflation works and also how the Higgs would behave during inflation if it were a light spectator field. Then I'm going to move on to discuss how we can calculate temperature fluctuations in the cases of perturbative inflaton decays, but also resonant inflaton decays. And finally, how we can also calculate the corresponding non-Gaussianity. So why do we need inflation? As I assume most of you know, inflation is a period of accelerated expansion in the very early universe. It solves a variety of cosmological problems. The most relevant for this talk, I assume, is the fact that it is believed that the temperature fluctuations that we observe in the CMB today are actually seeded by quantum fluctuation of the inflaton field, which drives inflation. In this talk, we're going to deal with a different mechanism for generating these temperature fluctuations, but more on that later. So the premise of inflation is that our entire universe is initially, observable universe is initially within the same moving Hubble horizon. So all regions of the universe are in causal contact with each other. But as the expansion begins, more and more scales start exiting the horizon. They stop being in causal contact. And eventually, at the end of inflation, what we're left with is around 10,000 causally disconnected regions, or Hubble patches as we call them. Now, in the slow roll paradigm of inflation in particular, this accelerated expansion is described as an inflaton field that slowly rolls along an almost flat potential. And the expansion ends when this inflaton field enters a regime of fast oscillations. And at the same time, during this oscillation, it reheats to standard model particles. And this period of decaying to particles is what we call reheating period. Now, how can the Higgs behave during inflation? So the Higgs can be a light spectator field during inflation. That is a very reasonable assumption. And if it is, then its potential would be something proportional to its self-coupling constant times the field value to the 4. So the Higgs field will initially be rolling classically down this potential, and eventually, after some time, it will reach the minimum, and quantum fluctuations will start pushing it over the minimum. And these quantum fluctuations are very interesting because they can actually stretch to superhorizon scales, and I will explain what that means. So as I mentioned earlier in the beginning, the moving Hubble horizon was so large that it enclosed our entire observable universe. So every single Hubble patch was actually in causal contact with the others. So even if the Higgs had some quantum fluctuations, then the Higgs VEV would still be the same at every Hubble patch because every Hubble patch communicated with the rest of them. However, as the moving Hubble horizon starts to decrease, more and more Hubble patches exit this causal region of causal contact. And as a result, because Higgs fluctuations stretch to the superhorizon scales, each Hubble patch outside the horizon acquires a different Higgs VEV compared to its neighbors. So at the end of inflation, you're left with 10 to the 4 Hubble patches, each of which is characterized by a different Higgs VEV, basically. And the probability of finding a Higgs VEV at some region in the universe is given by this equilibrium probability density function that depends on the self-coupling constant of the Higgs at the end of inflation and also on the Hubble parameter at the end of inflation. Now, after inflation has ended and during reheating, the Higgs starts to have a deterministic motion, which is just damped Higgs oscillations. So why is this important for the period of reheating? Why are Higgs dynamics during inflation important for reheating? And the answer to that is that during reheating, as I said, the inflaton has to decay to standard model particles. And if those particles are fermions, for instance, then these fermions will be acquiring their masses from Yukawa couplings to the Higgs. So you will have a fermion mass that is directly proportional to the Higgs VEV. And since you have a Higgs VEV that is different in different patches of the universe, then your fermion mass will also differ between different regions. And because your inflaton decay rate will also depend on the fermion mass, then you also have a space-dependent inflaton decay rate. Now, if you assume a Yukawa type coupling of the inflaton to fermions, then your decay rate will look something like this. Here I have plotted the decay rate for any value, really some value of the Higgs VEV, and also the evolution of the Higgs VEV as time goes by. This is N is the number of E-folds after the end of inflation. So the theta heaviside function over here essentially tells us that if at a particular part of the universe you have such a large Higgs VEV that it induces fermion masses that are much larger than the inflaton masses, then the inflaton cannot possibly decay to this fermion, and the decay is what we call Higgs blocked. So this is what happens over here, where the Higgs is quite large, and as a result your decay rate is 0. You can see that. Now, next we have the phase space factor over here, which also depends on the Higgs VEV through the fermion mass. And you can see that even in the absence of Higgs blocking, where the heaviside theta function is 1, this will also make the decay rate space dependent. And this is the region over here where the Higgs has decreased significantly so that blocking can be lifted, but it still modulates the decay rate quite a bit. And finally, we have the unblocked decay rate, which is the decay rate of the inflaton to these fermions when you have no Higgs blocking and no Higgs modulation, and you're somewhere over here where the Higgs has made the fermion mass much smaller than the inflaton mass. So your decay rate is practically gamma naught over here. So at the end of inflation, you not only have a bunch of Hubble patches with different Higgs VEVs, but because of that, each region of the universe also has different fermion masses, different decay rates of the inflaton to those fermions. And finally, they also reheat at different temperatures because the reheat temperature directly depends on the decay rate of the inflaton. And since you have a variation between different patches, you see adiabatic density perturbations. But these adiabatic density perturbations are additional to any adiabatic density perturbations seeded by inflaton quantum fluctuations that I was talking about in the beginning. Now, the name of the game is how do we calculate the temperature fluctuations associated with Higgs dynamics? So to do that, we started by sampling a number of n initial Higgs values from the equilibrium PDF at the end of inflation. Each of these values corresponds to a different Hubble patch. And we could then solve this system of 4 coupled differential equations at every Hubble patch over here. So you have 2 equations describing the evolution of the energy densities. You have 1 equation describing the damped Higgs oscillations after inflation, and equations describing expansion dynamics via the Hubble parameter. So if you solve this system at every Hubble patch, you can find the value of H at every Hubble patch at every E-fold after inflation. Or in other words, you can determine the evolution of the Higgs PDF at every E-fold after inflation. And the PDF is essentially the probability of having a particular Higgs value in the universe. So this is what it would look like. You have the PDF at the end of inflation, after 1 E-fold, after 2.5, and after 6.5 E-folds after the end of inflation. And note that the horizontal axis over here is actually shrinking in size, and that is reasonable because, as I mentioned before, after inflation, Higgs oscillations are damped, and as a result, at every Hubble patch, Higgs values tend to decrease further and further with time. So the width of the PDF will also decrease with time. Now, Since we did not want to calculate a full distribution of temperature fluctuations in order to be more computationally feasible, we defined a characteristic value of the Higgs PDF as just the standard deviation of the PDF, since the mean of the PDF is always 0. And we could then define a background decay rate averaged over all Hubble patches and independent, space independent, as the decay rate at that particular characteristic value, and also the perturbation over the decay rate at just the variation in the decay rate over the background, again at this characteristic H tilde value. And this is really cool because this way we can actually use these perturbed Einstein equations that were introduced by Dvali et al. In 2003 and find the evolution of the Bourdin parameter with time. So here you have two equations describing the evolution of the adiabatic density perturbations. Over here you have the equations describing the evolution of the background energy densities. And finally, you have a differential equation for the evolution of the gravitational potential perturbation with time. So if you solve this system of 5 coupled differential equations, you can actually derive zeta as a function of the folds after the end of inflation. And this is extremely useful because for larger scales, this Bourdin parameter zeta is directly proportional to the temperature fluctuation it corresponds to. So the delta T over T induced by the Higgs will just be the Bourdin parameter over 5. And a rather typical value for the self-coupling of the Higgs at such high energy scales as the inflation energy scale is 10 to the minus 2 in the standard model. So we took this value and plotted this 2D parameter space of the unblocked decay rate versus the range of Yukawa couplings, and we could then use Planck data to constrain this parameter space. So the red region corresponds to a delta T over TH that is larger than Planck observes. And then you have the white region, which gives delta T over T exactly the same as Planck observes. And finally, the green region over here is always smaller than observations. So in principle, the white and the green regions are allowed by observations. And if you want to take it one step further, you can also plot this hatchet region where the delta T over T is actually smaller or equal to 10 to the minus 7. And this region is of course allowed, but if you look at parameters over here, you will never be able to observe any Higgs contribution to the temperature fluctuations of the CMB because you are below the sensitivity, the 1% sensitivity of Planck. Note over here that if we chose a lambda I that is smaller than 10 to the minus 2, for instance 10 to the minus 3, we would be able to constrain our parameter space even tighter because the temperature fluctuations become larger as you go to smaller self-couplings. Now this, what I have mentioned so far, was all for perturbative inflaton decays, but it's also very interesting to look at resonant preheating after inflation. So for that purpose, we assume Chern-Simons couplings of the inflaton to gauge bosons, and these Chern-Simons couplings, they are very useful because when the inflaton is, for instance, an axion in models of natural inflation, these are the kind of couplings you would get. So these gauge bosons will also be acquiring their masses from gauge couplings G to the Higgs. The only difference is that you cannot define a decay rate in this case because it's no longer perturbative decays. It is very important to note that we wanted all our Hubble patches to actually finish reheating via resonant decays, because if some Hubble patches finished reheating via resonant decays and some others via perturbative decays, then the differences in reheat temperatures would be many orders of magnitude. And that would lead to temperature fluctuations of order 1, which we know for sure that they are excluded by observations. And so there was not really any point in looking at those cases. So we concentrated actually our calculation for a range of masses around here and for a relatively slow decay constant F, so that preheating is completed in every Hubble patch that we look at. Now, the method is quite similar. We again have distribution of Higgses, which gives a distribution of gauge boson masses, and we can then solve the equation of motion of the gauge bosons, ignoring back reaction of the gauge bosons to the inflaton field, and determine the energy density in the inflaton and the energy density in radiation at every one of those patches with time. Then we could again define some characteristic values for the adiabatic density perturbation, and the background, of course, is just the average of the distribution. And if you plug those equations into the differential equation for the gravitational potential and the equation for the Bardeen parameter evolution, you can in fact plot the Bardeen parameter with time, like you could before. So here we plotted for two extreme values of the gauge coupling. One is quite low and the other one is quite large. You can see that even for a gauge coupling of 0.1, which is quite low in standard model terms, the delta T over T that you would get is already 10 to the minus 4, which is slightly larger than what Planck observes. So you can actually exclude resonant decays of the inflaton to these Higgs gauge bosons. And note also that the main increase of the Bardeen parameter happens within 1 E-fold after the NM inflation. So our choice of ignoring back reaction of gauge bosons to the inflaton field is actually quite reasonable. Now, since we have excluded resonant decays, we can move back to perturbative decays and actually try to calculate the non-Gaussianity. And for that, we use a method we call patch by patch. And it starts quite similarly to the other one. So we again sample a number of n Higgs values from the equilibrium PDF. And we do solve the system of 4 coupled differential equations. However, we do not aim at deriving the Higgs PDF at every E-fold after inflation, but rather than that, the energy density PDFs at every E-fold after inflation. That is really useful because it gives us the opportunity to actually use these very simple definitions for the background and the perturbation over the background. So the background will just be the mean of each of these distributions, of course, the average, and the perturbation over the background at a particular patch would just be the value of the energy density at this patch minus the background over the background. So the simplest definition for the adiabatic density perturbations you have. And this would give you a distribution of adiabatic density perturbations, and of course that would lead you to have a distribution of gravitational potentials and Bardeen parameters with time. And since the Bardeen parameter is proportional to the delta T over T for larger scales, then you would be getting a distribution of temperature fluctuations this time instead of a characteristic value of the temperature fluctuations. And here you can see this distribution after 1 E-fold, I think 3 E-folds, and 8 E-folds after the NM inflation. And you can see how the width of this distribution is growing because your temperature fluctuations are still growing and evolving. And at some point they will stabilize when this evolution stops. Now, having a distribution is very useful because you can actually derive the nonlinearity parameter FNL. So what we did was we defined FNL like Planck does. However, we could not use the bispectrum because we have no information on smaller scales whatsoever. We only have a 1-point Higgs PDF. So we actually calculated a higher moment of distribution, which is the skewness, and took FNL to be the skewness of these Higgs-induced temperature fluctuations over 6 times the delta T over T to the 4. And there were 2 assumptions that were made. First, that the skewness is dominated by reheating dynamics rather than slow roll dynamics, which is quite reasonable because slow roll inflation only produces an FNL of 10 to the minus 2, which is very small. And also that the delta T over T should be 10 to the minus 5, which is observed by Planck, and we know, of course, to be correct. So if you do this calculation, you can constrain parameter space even further. So you can see how the bounds tighten for the from the white region to this minus 70 line, which translates into sometimes even to an order of magnitude when you look at unblocked decay rates gamma naught. So the minus 70 line is actually the lower bound by Planck, which would normally be minus 6. However, we have to ease it by a factor of around 10 because we only look at larger scales. And everything below this line is allowed by observations. Now, the -1 line is something quite different. So it's sort of a bound that comes from observability, because we know that any contribution of FNL below order 1 will always be amplified to order 1 by secondary effects, such as gravitational effects that happen even before CMB decoupling. So if the Higgs were to produce an FNL that was found in this region over here, you would not be able to tell by observations when you detected this order 1 FNL, you would not be able to tell if this comes from the Higgs, slow roll, or any other kind of very, very small effect. So your only area of interest is between these two lines, actually, these black lines. And I will leave you with some conclusions. We have established that a light spectator Higgs during inflation can actually cause significant temperature fluctuations and significant non-Gaussianity. And we have shown how we can compute those and use Planck to constrain our parameter space. We have excluded resonant decays of the inflaton to standard model Higgs gauge bosons. And we have found a region of interest for future observations and future instruments of non-Gaussianity. And we should also say that a future study of scale dependencies of these distributions can actually provide more accurate results and constrain parameter space even better. So thank you.